Okay, so let's talk about a mass spectrometer. So it's made of two parts. This part is called a velocity selector, and then this is sort of the bigger chamber, okay? So the idea is that you send an ion in with, some velocity, v. Sometimes you'll see things that say that they send in a doubly ionized, so doubly ionized particle. All that means is that the charge is 2e. If it's a negative doubly ionized particle, then it'll be negative 2e. But I just wanted to tell you about that that phrasing that they sometimes use. Okay, so in this velocity selector, I'm going to draw an electric field this way, and there's a magnetic field perpendicular to that. Okay, so that's the B field, and then the red is the E field. Okay, so I want you to imagine you have this particle, okay, and it has a charge Q, and it's in the electric field and a magnetic field. Okay, so what do you think this charge will feel? Well, it's going to feel a force due to the electric field. Okay, I'm going to redraw the charge over here, and I'm going to use the color coding in the same way. So if this was let's say this is a positive charge, okay? Gosh, that's beautiful. A positive charge, what is the direction of the force that it'll feel from the electric field? Hopefully you recognize, right, that it's of the form QE, and the force will be in the same direction as E. So now for the force due to the magnetic field, remember that it's moving to the right, V. So when we do F equals QV cross P for the magnetic force, remember we have a right-hand rule, and so the V is this way, the B is this way. So using the right hand, my fingers go along V, and B is coming out of my palm. So that I sweep my fingers into that direction. And so that means that gives me that. So let me just draw that on here. And that has the value QVB because our V and our B are perpendicular, so there's no sine theta to worry about. So the idea with this velocity selector is that I have a very, very small hole on this side. And we're interested in the ones that are going straight through. And so if that's the case, then the net force on it has to be 0 if it's going to go straight through, right? Which means that those two magnitudes have to be equal. So QE equals QVB. So we can dial our values of the electric field and our magnetic field in this region so that we get a very particular velocity of particle that goes straight through here. Okay? Cool. What would happen if I sent in a particle with a speed greater than that dialed up? What do you think would happen? Well, that the magnetic force, which is this one down here, would be bigger, right? Because that's the one that depends on V. And so as this went down, it would deflect down. And of course, you can make, all the logical arguments about V being less than E over B. It would deflect up. What if I send a negative charge in? Well, if my electric field was up and my B field was out, and this was a negative charge, then let's color code, shall we? My force due to the electric field would be down, and then right-hand rule it, right? If your V is this way, so your magnetic force gives you down, but then if it's a negative charge, then it will be up. So you get exactly the same relationship for positives or negatives. It's just the actual directions of the forces are flipped, so that this V is greater than E over B for a negative charge would deflect up. Okay, so that's the velocity selector, is that we dial in these E's and B's so that we know exactly what velocity that thing is coming out here. Okay, so we know that velocity. And then the simulation that we were playing with today, let's do some more B fields. Let's, just for fun, let's make it a B field in. And let's say this is a positive charge. Which way would this thing go? Let's do right-hand rule. My fingers are along V, and I have my palm. The B field is coming out of my palm, and so my thumb is gonna point up. And so we'll get something like that, right? So we talked about that in class, where you get this centripetal force provided by the magnetic field. And so that QVB is mv squared over r. And so if you move this around, so we can kind of look at, how would this be used? We know the velocity of the things coming in. You can measure the radius, and then, you know the magnetic field that you're putting in there. And so very often, the charge to mass ratio is the thing that they often talk about for particles. But anyway, these can be used in a variety of different ways, and they're actually a very doable AP type problem, so which is why I'm showing you. Okay, the other thing I wanted to talk about today, which I didn't get to, is forces on currents. All currents are moving charges, right? And so you shouldn't be surprised that there's a magnetic force, right? If I think about a charge and it's moving, you can equivalently think about it as the conventional current that way, right? So if we actually want to calculate this, the V is the distance over time, right? So if I wrote this as Q and then sort of the distance traveled divided by the time, and then that's my B field, Q over D, that's I, right? And then that distance is sort of a length of wire. So this is how we write it. IL cross B is the force on this is the force on a current I in a magnetic field with a magnitude B. And then this is the length of wire in the B field. Because you can have like regions of B field, and then you have like a long wire. It's only going to be this length that's in it, okay? And then this I is a vector, right? And again, that's the direction of the conventional current, so that's really the direction of positive moving charges.